We're going to be looking at a last set of tests to determine whether a series converges or diverges. There's two tests here, the ratio test and the root test. Both of these are tests for absolute convergence. So they will tell you that it converges absolutely. And of course, if it converges absolutely, that means also that the series itself converges. So both the absolute value and the series itself converges is what that means. And then also, when we look at these tests, they're just trying to tell us that it converges or diverges, or these tests could also be inconclusive, but they only are used to determine, again, series convergence or divergence. They do not determine the value of a series. So they can't say it converges to 2/3 or it converges to infinity. It just says converge or diverge. That's what we have going on here. So to get started, I would like to look at the ratio test first. So the ratio test has some particular functions that it's good for. It's really good for factorials. So if you have a problem with a factorial in it, it might be that the ratio test is the thing to use. Now, let's do a quick review of factorials. 5 factorial is 5 times 4 times 3 times 2 times 1. So whatever integer I start with, I decrease by 1 and then multiply down until I get to 3 times 2 times 1. 1 factorial is just 1, and 0 factorial is also defined to be 1. So a couple quick things. If we use a generic n factorial, that would be n times n minus 1 times n minus 2 times n minus 3, all the way down to 3 times 2 times 1. 2k factorial, you have to be careful here because the 2 is in the parentheses, so this would look like 2k times 2k minus 1 times 2k minus 2, all the way down to 3 times 2 times 1. But if you did 2k factorial where the 2 is not part of that, I would have 2 times k, k minus 1, k minus 2, all the way down to 3 times 2 times 1. So these are very different problems whether I have parentheses there or not. Now if I had something like 2 times the quantity k plus 1 factorial, now notice here the factorial is outside the brackets. So I could simplify within the brackets first, so I'd have 2k plus 2 factorial. And then when I rewrote this, this would be 2k plus 2 times 2k plus 2 minus 1, which would be 2k plus 1. 2k plus 1 minus 1 would be 2k, and then of course 2k minus 1, and this would continue on to 3 times 2 times 1. So hopefully these are a little bit familiar to you working with factorials. Another neat thing about factorials are they cancel, and we're going to be using this property a lot. N plus 3 factorial is n plus 3 times n plus 2 times n plus 1 times n minus 1 down to 3 times 2 times 1. N factorial that's in the denominator right here, that's going to be n times n minus 1 times n minus 2, all the way down to 3 times 2 times 1. Well, what we could have done up here in the numerator is this bit right here, n minus 1, that's just n factorial. So I could have just canceled this n factorial with this, and this would have just left me with n plus 3 times n plus 2 times n plus 1. So that would have simplified. So that's a quick little review of factorials. If they're not as familiar with you, you will get a lot of practice when we're working through these. So let's go ahead and write out the criteria for the ratio test. So for the ratio test, what we do is we go ahead and let our series a sub k be an infinite series. So again, that means my upper indice here would be infinity. And we have all positive terms. and let R, and sometimes you'll see this also as rho, you'll see it kind of defined either way, both means the same thing, equals the limit as k approaches infinity of the next term divided by the current term. So a sub k plus 1 would be the next term, a sub k would be the current term. So next over current. Well, we have three things that can happen here. One, this value of R, if it's less than 1, then the series converges absolutely. And if it converges absolutely, we can just say also that it converges. So a lot of times, unless you're asked specifically for absolute convergence, you can just say convergence there. Next case, if R is greater than 1 after I take that limit, and greater than 1 includes infinity, because it doesn't say finite, the series diverges. Okay, and the last one, if R equal 1, the test is inconclusive. Okay, so that is the ratio test. I'll write that up top here, just to keep the name of the test nearby. So we're going to run a few ratio tests, and then I'll show you the root test, and we'll do a few of those. Actually, you know what? I think I will just do the root test right now. So then we'll have them both done, and then we can just run through a lot of problems and then decide kind of as we bounce back and forth which test to use. So the root test, the ratio test was really good for factorials. It's good for other things as well, but it's really good for factorials. The root test is good for, as you might say, roots. So square roots, cube roots, kth roots, that type of thing. So let's go ahead and let our series a sub k be an infinite series with non-negative terms. So non-negative is different than positive. Positive means greater than 0. Non-negative means greater than or equal to 0. And we have this value of rho, and we talked about the rho up here. So rho, or R, would equal to the limit as k approaches infinity of k, the kth root of a sub k. So we have three things that can happen. One, if rho or R is less than 1, the series converges absolutely. Or we can just say converges as well. Second, if R or rho is greater than 1, the series diverges. And of course the third case is going to match. If R or rho equals 1, the test is inconclusive. Okay, so that's what we have going for us so far, the ratio and the root test. And it's on your formula sheet for Unit 3, so you can always refer to that because it's nice to have all those tests in one spot. So let's go ahead and work through quite a few problems, and then also toward the end we're going to get into a little bit of a new topic. We're going to find intervals of convergence. Now some of these problems can get a little bit long because we have a lot of simplifying to do when we set up the ratio. Now this says to use the ratio or the root test. This one, you could use either one. I'm going to choose the ratio test because of the factorial. So the ratio test. So remember, for the ratio test, what we want to do is we want to set up a limit where we look at the next term divided by our current term. So let's go ahead and set that up. So first of all, this is infinite, and it's a series. In this particular case, we're looking at a series of terms that are all, you know what, I just remembered when I was saying that, I'm taking the absolute value here, so let's go ahead and pop back up here and put in these absolute value signs. Okay, so with the ratio test, you need to make sure you have those absolute value signs, because then it doesn't matter if I have negative terms. When I take the absolute value, I just consider them as positive. And the same thing will happen with the root test. The absolute value is inside the parentheses though. So that takes care of problems if I'm taking even roots of odd numbers. So let's look at the ratio test. So the ratio test, I'm looking at my value for r is equal to the limit as k approaches infinity of the next term, the absolute value of my next term divided by my current term. So the next term, basically all my values of k, I would replace with k plus 1. So this would be negative 22 to the k plus 1 all over k plus 1 in parentheses factorial. So that's the next term divided by my current term, and the current term is what's listed here. So negative 22 to the k all over k factorial. Well, we want to do a lot of rewriting here. We want to get rid of these layered fractions. So when you divide by a fraction, you multiply by the reciprocal. So I get negative 22 to the k plus 1 k factorial, because this is going to flip. In the denominator, I'll have negative 22 to the k all over k plus 1 factorial. So that's what I have here. Now let's recall some different properties of exponents here. So I have the limit as k approaches infinity. So absolute value of negative 22 to the k times negative 22 to the first k factorial. In the denominator, I have negative 22 to the k, and then I have k plus 1 factorial, which is going to be k plus 1 times k factorial. Now, a lot of things cancel here, the k factorials, the negative 22s to the k power, and then I'm left with the limit as k approaches infinity, and the absolute value of negative 22 is just 22, so I'm left with 22 over k plus 1, and this is equal to 0. Because the degree in the numerator is less than the degree in the denominator. Well, if I get that this is equal to 0, that's up in the first case here, where r, or rho, is less than 1. So r is equal to 0, which is less than 1. Therefore, it converges absolutely. So quite a bit of simplification there. Now again, remember k plus 1 factorial is k plus 1 times k minus 1 all the way down to 3 times 2 times 1. This piece right here is k factorial, so that's why that cancels. Okay, so we use the ratio test on that one. Next one, they give us the option of the ratio and the root test again, but this one lends itself to the root test very nicely because of that kth power. So if I take the kth root of the kth power, those roots end up canceling with the power. Okay, so let's have a look here. So again, I'm seeing that I have a power here. So if I take the kth root of, let's say, x to the k's cancel each other out and I'm just left with x. So that's kind of the idea of using the root test here. So let's look at the root test. So for the root test, what I want to do is I still want to take a limit, and I'll take the limit, and that's going to be my value for r or rho, however you want to look at that. And I'm going to take the limit of the kth root of all of that raised to the kth power, and it's the absolute value. So because it's the absolute value, I don't really have to even worry about this piece right here. So let's go ahead and look at r or rho. They tend to use rho for the root test and r for the ratio test. And this would be equal to the limit as k approaches infinity of the kth root of the absolute value of all of this. Now, because it's the absolute value, I could just ignore this negative 1 to the k plus 1 and all that because it's going to cancel, but I'll just put it into this first one just so you realize kind of what's happening with that. And this is raised to the k power. So because it's the absolute value, that entire negative 1 to the k plus 1 goes away. And all values of k are positive, and I have all positive values in here. So if I wanted to, I could just kind of forget about my absolute value signs. Now that's not always the case, so don't arbitrarily just stop using them. It depends on the function that we're given. So all of this is raised to the kth power. So what ends up happening is the kth power and the kth root cancel, and I'm left with the limit as k approaches infinity of 7k to the 5th plus k all over 4k to the 5th plus k plus 4. And this is equal to 7 over 4 because the degree in the numerator is equal to the degree in the denominator. So the limit is the ratio of the leading coefficients. Now since rho is equal to 7/4, I can go back up and compare that on my root test, and 7/4 is greater than 1. Therefore, the series diverges. Now I could have tried to use an alternating series on this and establish that this is non-increasing, but that would be really difficult to do. This one lends itself really nicely to the root test. So this one, I can use the ratio test, it says. So let's go ahead and follow those instructions. So the ratio test, I'm going to define r, our rho, to be equal to the limit as k approaches infinity of the absolute value of our next term, which would be k plus 1 quantity squared all over 6 to the k plus 1, divided by my current term, which is k squared over 6 to the k. Now everything looks to be positive here because k is going from 1 up to infinity. So I could drop those absolute values, but I'm going to wait until after I simplify this just a bit in case something strange might pop up. So when you divide by a fraction, you multiply by the reciprocal, so that 6 to the k will come up. And then I also have 6 to the k plus 1, and then I have k squared as well. So simplifying further, I have the limit as k approaches infinity, and now I can clearly see that I'm going to have all positive values here, so I'm going to drop that. So I'm going to have k plus 1 quantity squared, 6 to the k, and then the denominator k squared, and then 6 to the k plus 1 is 6 to the k times 6 to the first, because when you multiply like bases, you add exponents. So simplifying just a little bit further, I'm going to have k plus 1 quantity squared, I can get rid of those absolute values, would be k squared plus 2k plus 1. It's just going to be some k squared stuff. I really only care about the highest power. If you want to write it out, you can. In the denominator, I'll be left with 6k squared. So when I take that limit, I'm going to be left with 1/6. Why? Because the degree in the numerator is equal to the degree in the denominator. So the limit is the ratio of the leading coefficients. Now again, this wiggly line just represents all that stuff multiplied out because I only care about the highest powers. So I have 1/6 here as my limit, and 1/6, if we look at the ratio test, is less than 1. So r equals 1/6, which is less than 1. So therefore, this converges absolutely. Okay, so that's kind of the conclusions that we're trying to draw on these. Now this one looks like a good spot for the root test as well, because I have kth powers on both the numerator and the denominator. So they are telling us to use the root test. So again, we name our test, and then we look at the criteria for the test. So rho here, or r, would be the limit as k approaches infinity. And I would use the kth root here. And the reason I'm going to use the kth root is it'll cancel with the k in the exponent. So this would be the kth root. And for the root test, I would have k to the k over 10 to the k. So if I wanted to, I could rewrite this. I could take the root right now. And of course, this is absolute value, but all my terms are positive, so I can drop that. So I could have the kth root of k over 10 to the k. So what ends up happening here, and again, this is absolute value, but all k's are positive here. These k's cancel each other because one is a power and one is a root. So I'm left with the limit as k approaches infinity. Gosh, I'm just left with k over 10. And of course this is equal to 0 because the degree in the numerator is less than the degree in the denominator, so I always have to include that. And so if I look at this, my value for k, since k is equal to 0, actually I just messed that up. I was thinking k was in the bottom, but in the denominator, but it's actually in the numerator. So since k is in the numerator, this is going toward infinity. Why? Because the degree in the numerator is greater than the degree in the denominator. So what I have here is rho equals infinity, which is greater than 1. Therefore, the series diverges. So that's my conclusion there. So watch out for this. Don't make that same mistake I did there. I'm so used to the k being in the denominator, I didn't even really pay attention to that. Now this is an interesting one because they're telling us to use the ratio test, but not what to use the ratio test on. So what I need to do is I need to rewrite this in terms of a series. So I'm going to go k equal 1 to infinity, and it looks like my numerator goes 2, 4, 8, 16. So these are powers of 2. So this is be 2 to the first, 2 squared, 2 cubed. So I think that would be 2 to the k in the numerator. And the denominator is not as clear. So if I'm looking at 2, 2, 4, 8, 16, 32, 64, that would be 2 to the 6th. This would be 1 to the 6th. This is 3 to the 6th. This is 4 to the 6th, etc. So this would be k to the 6th. So that's the series that I'm trying to test here. And it says I'm using the ratio test. So let's go ahead and write out the test, name the test. And then let's go ahead and perform the test. R is equal to the limit as k approaches infinity of the absolute value, and of course the absolute value is not going to be needed here, of the next term divided by my current term. So again, I don't need the absolute value because all my values of k are positive and all the terms are addition. So k approaches infinity. So I'd be left with 2 to the k times 2 to the first times k to the 6th. Because remember, when you divide by a fraction, you multiply by the reciprocal. So in the denominator, I have 2 to the k times k plus 1 to the 6th. So again, when I take this fraction, when I divide by this fraction, I multiply by the reciprocal, so it reciprocates up top. So a lot of things cancel here. The 2 to the k's will cancel, and then eventually the k's to the 6's will cancel, but I'll show you what that will look like. So I have the limit as k approaches infinity, and I shouldn't say cancel, we'll disregard them because the degree in the numerator and the degree in the denominator will be the same. So in the numerator I have 2k to the 6th. In the denominator, I don't want to take k plus 1 to the 6th power. I don't want to take k plus 1 and multiply it by itself 6 times. So what I do is I say, oh, I'll have k to the 6th plus all these other terms. So now I can compare the degree in the numerator and the degree in the denominator, and I get 2 for my limit because the degree in the numerator is equal to the degree in the denominator. So r is equal to 2, which is greater than 1. And if I have greater than 1 here, that would tell me that the series diverges. I like these problems because you get to do a lot of algebra, kind of the layered fractions and canceling. So these are kind of fun problems. So here they're asking us to use the ratio test again. And with the ratio test, they're looking at answering the question, does this converge absolutely or diverge? Those are our two options here. So I think what I'd like to do, I'd like to rewrite this. So let's go ahead and rewrite this. Let's go k equal 1 to infinity. And that would be k over e to the 14k. I'm going to rewrite that so it's a little bit easier to read. Okay, so that's what we have here. So to the ratio test, I'm going to name my test. All my terms are positive, so I don't need to worry about the absolute value, so I have r here. And r is the limit as k approaches infinity of the next term, k plus 1, over e to the 14. Now be careful how you write this. I'm going to make a little side note here. If I do 14k plus 1, that's wrong. It should be 14 times the quantity k plus 1. Okay, so be careful how you write it. This is wrong. This is right. So that would be 14. Again, I want to rewrite that a little bit. 14k plus 1. All over our current term, which is k over e to the 14k. Okay, so technically there's absolute values here, but all of these terms are positive. There's no negatives here. So I can drop those. And remember, when you divide by a fraction, you multiply by the reciprocal. So e to the 14k comes up top times k plus 1. And then in the denominator, I'll have e to the 14 times the quantity k plus 1. And remember, it's not just 14k plus 1, it's 14 times the quantity k plus 1 all over k. And of course, we have some simplifications that we can do here. So I have 14 e to the 14k times k plus 1, so that's not going too far there. And then in the denominator, I'm going to have e to the 14k times e to the 14th times k. Because remember, when I take this 14 times k plus 1, that's going to give me 14k plus 14. And then when you raise a power to a power, you multiply the powers, but when you multiply like bases, you add the exponents. So that's why I can split that up. So e to the 14ths cancel, e to the 14k's cancel. So what I'm left with here then is the limit as k approaches infinity of k plus 1 over e to the 14th times k. Well, this is going to equal 1 over e to the 14th because the degree in the numerator is equal to the degree in the denominator. So our limit is the ratio of the leading coefficients, which is 1 over e to the 14th. Well, this is a very, very small number. It's definitely less than 1. Therefore, the series converges absolutely. So there's our conclusion. So a lot of simplification there. Okay, so this one doesn't tell us what test to use. It just says use the appropriate test. So I could use the divergence test to start with, but it's hard to compare with our factorials and with this fourth power. So I really think that the important thing to do here is to go right for the ratio test because of the factorials. But remember, we do have that list. I should start with the divergence test, geometric series, p-series, integral test. I have the alternating series test, direct and limit comparison, and the ratio and root test. But I'm going to use the ratio test because of the factorials. So there's no negatives here, so I don't need the absolute values. I don't have anything alternating or negatives that are popping in here. I'll just throw them in so we can remember that they're actually there. And I'm going to be left with k factorial to the 4th. Actually, it's going to be k plus 1, sorry. Factorial, and then that's to the 4th, because this is my next term. We have to be careful how we write this, k plus 1 factorial divided by my current term, which would be 7k factorial to the 4th, all over 8 times 4k factorial. So a lot of simplification here. So let's look at the limit as k approaches infinity. And I'm going to distribute first and flip as well. So again, when you divide by a fraction, you multiply by the reciprocal. So here I'm going to have 7 times k plus 1 factorial, and that k plus 1 factorial is to the 4th power. And then this piece down here, right here, when you divide by a fraction, you multiply by the reciprocal, that flips up top. So that would be 8 times the quantity 4k factorial. So then in the denominator, I'm going to have 8 times 4k plus 4 factorial times 7k factorial to the 4th. Okay, this is looking kind of ugly here, so hopefully this will simplify quite a bit. So we have the limit as k approaches infinity. I'm going to drop the absolute values because all my terms are positive. So in the numerator, I see I have 7 times 8 is 56. And then I have a 4k factorial. And again, the 4 is with that factorial as well. And then I also have a k plus 1 factorial to the 4th. And hopefully something will cancel there. And then in the denominator, I have an 8 times 7 is 56. And then I have a k factorial to the 4th. And then I also have this 4k plus 4 factorial. So I've kind of cleaned things up a little bit. The obvious thing to cancel are the 56's. And now all these factorials I need to figure out as well. Okay, so here we go. Let's rewrite and simplify this a bit. So this is the limit as k approaches infinity. And remember, this is our value of r for the ratio test. So 4k factorial. I'm just going to leave that as is. And then x plus 1 factorial to the 4th power. So this would look like x plus 1 times x. Now that x is a factorial, because I could keep rewriting this as x, x minus 1, x minus 2, x minus 3, all the way to x, or sorry, all the way to 3 times 2 times 1, but I can just summarize that with an x factorial. And then here, I'm sorry, I'm mixing k's and x's. I need to be all k's here. So this is k plus 1, k plus 1. And then I have k factorial to the 4th. And then over here, I have 4k plus 4 factorial. So rewriting, this is a good one. I have 4k factorial, and remember it's quantity factorial, not just the k. And then I can take this exponent. I can't do this with addition or subtraction, but I can do this with multiplication and division. I have k plus 1 to the 4th, and then I have k factorial to the 4th. And then in the denominator I have k factorial to the 4th. And then I also have this 4k plus 4 factorial. Now I get some more things to cancel, so that's good. The k factorials to the 4th cancel. And let's go ahead and rewrite and simplify some more. So the limit as k approaches infinity. Now let's think about this one. So I have the 4k factorial, quantity factorial, the k plus 1 to the 4th. But in this denominator, I have 4k plus 4 factorial, which would be 4k plus 4 times 4k plus 3 times 4k plus 2 times 4k plus 1 times 4k factorial, quantity factorial. So these cancel. And what I'm left with here then is the limit as k approaches infinity of k plus 1 to the 4th. Well, I don't want to multiply that out, but that tells me I'm going to have k to the 4th plus some stuff, other terms. And then in the denominator, I don't want to multiply this out either. But if I do multiply it out, I get 4 times 4 is 16 times 4 is 64. 64 times 4 is 256. So I get 256k to the 4th plus some stuff if I just look at those first terms. So when I take my limit, I get 1 over 256. Why? Because the degree in the numerator is less than the degree in the denominator. Sorry, is equal to the degree in the denominator. So r is equal to 1 over 256, and that is definitely less than 1. Therefore, the series converges absolutely. This is a fun one. So series converges absolutely. Lots of simplifications with the factorials. So you have a lot to keep track of with these problems, and leave yourself plenty of room to show your work. And again, on exams, you'll want to make sure that the more work, the better. If you skip steps, it's hard to give you partial credit if you come up with the incorrect answer at the end. As usual, if you have any questions, please let me know, and good luck and enjoy working on these.